All right, welcome back. So in the last video, we were just talking about the general anatomy of these coefficient estimates, okay, and what they tell us, right? So we were able to kind of extract these values and put them into something that makes a little bit more sense as far as the equation of a line, right? So based on the data that we have here, we're able to say that essentially there is a negative relationship between age and density, right? As age increases here, muscle density will decrease on average by 1.19. Okay, so that's pretty much that. But are we able to trust the model, right? Very similar to ANOVA, we've got some stuff that we have to check just to make sure that everything here is going right. Okay, so this whole thing, this whole thing, right, is what you'll be given. And you just have to kind of filter through and get all the right stuff, right? Get all the good stuff. So we've got this one last little part here that we'll talk about. And thankfully, let me just kind of cross out what we do need and what we don't need. We don't need that. We're going to ignore that. We're going to ignore this. And we're going to like kind of partially ignore this. So really all we're doing, right? So we're not even going to worry about this. What we're doing, right, is we're just trying to figure out the relationship between our two variables, right? X and Y, okay? Muscle density and age in this case. Okay. But one thing, there's another thing that we can calculate, quote unquote, the computer calculates for us, and it's this R squared, this idea of R squared. And the first thing that we can tell by it is how well our data fit around the line, okay, that we drew. Okay, so this is like sort of the first checkpoint, right, for how well our model is doing. Okay, and what this value is actually just right here, right there, 0.751, 0.7501. Wow. Okay, and so R squared is only, excuse me. Okay, it's only between 0 and 1, okay, and it can be only between these two values. It's not going to be negative, it's only positive and only kind of like a fraction, right? And what this tells you is how much the variation of y is being explained by our predictor variable, right? So in this case, how much of the variance is being explained, right? How much of the story essentially is being told? How good is X doing at explaining why is essentially what's happening. Well, the whole story, out of the whole story, 75% of the story is being told by our single predictor, which is pretty good, I think. 3/4 of the information being covered by one thing, that's not bad, right? That is not bad. Adjusted R squared, you can read that for yourself, but that's a class, that's the next class. That's stat 3050. And then our p-value, we get a p-value for the whole model, right? So we get p-values here, right? This is what we care about. We care about big time, care about these two p-values, right? P-value for each. Can we trust that this value is actually this value? Can we trust that this value is close to the actual value? And if this is less than 0.05, then yes, it is. What this p-value tells you, it's like kind of like the second stop of how well your model is doing, right? This is just kind of judging the overall process, right, of what the computer was doing, okay? So, again, you don't get a whole lot of like interpretable information out of that, but it does, kind of support the fact that your process is correct, right? Or at least the computer's process. So, how much variation is being explained by X? Look right here, 75%, right? Which is pretty good, right? The higher the better, too. The closer you are to 1, the more of the story is being told by your predictor variable, which is great. But just like in ANOVA, we've got some places where we're a little wrong, right? We have that residual stuff that we could plot, right, and see what that looks like too. Okay. So that brings us to the next kind of part of this, where we're going to be looking at a couple of different plots, mostly just the scatter plot and histogram, but we've got to do a little bit of kind of critical thinking, a little bit of judgment, right? So no biggie. Okay, so the first thing that you have to do, the first thing whenever you're drawing this, right? Whenever you have data, and it looks like this, and then you're drawing a line through it, there's two things for this class. There's two things that you got to make sure are happening, right? The first thing is the goodness of fit, right? So our data here, let me get rid of the line. Our data here existed before we drew a line through it, right? So that's no big deal there. But what we're doing is that we are then imposing how we think everything works with this line, okay? But we can only do that. We can only do that if the data appear linear. Actually, I was going to say straight line. We're just going to leave it as linear, right? So if, and there's another example here in just a second, but if our data, right, looks like this, right, the computer still is going to try its very best to draw a line through this, okay? But we see, and hopefully I drew it good enough, that it's very much curved, right? So when our computer draws the line through it, it's legitimately drawing the line the best that it can. It's still the best fit line, okay? But we're not going to be able to trust the equation, right? Because our data is not in a line. Our data is in this kind of curved fashion, right? Okay, so that's the first thing you want to check for. The data have to be at least seemingly linear, okay? And no curvature like this. No curvature like that. Okay, so no biggie. The next thing that we want to look for is, seen this before, a normal distribution of the residuals. And that's just going to be given to you as a histogram, right? So you have to do a little bit of kind of, I don't know, nitpicking with that picture, with that figure, but otherwise it's the same as what we did last week, right? With the ANOVA. So normal distribution, residuals must be normally distributed. And that's easy, right? That's easy to kind of look for. Because that's going to be given to you. Amen. Amen. All right, so what does goodness of fit look like? Well, it looks like this. So the data existed before, right, before we drew the line. But then when we drew the line, right, it's doing a pretty good job, of sticking to the data. Or at least the data are doing a pretty good job of sticking to the line, right? Okay, so we'll just make sure that this is still in our heads. Okay, still there, right? And then we're not seeing any kind of curvature or anything like that, right? We're all okay. Here are some examples of some bad fit, right? So this is what, over here especially, our data, right, existed before we drew a line through it. And it just so happens that when we plot these two things together, they make this curve, right? Way up here. And then when our computer says, okay, I can still draw a line through this, it's going to be way off, right? We're not going to be doing a very good job of estimating, or at least of sort of suggesting the relationship between these two things, which is no good, right? No good. Our line has to fit the data pretty well, okay? And we see the same sort of story over here too. It's a little bit more subtle, but we can kind of see, and this does take some practice, just experience, but there's a little bit of that kind of curvature going on there that is no good. So the line that we're drawing is still legitimately calculated by the computer, but the computer assumes already that the data are linear, which in this case, it is not, right? We would have to do something else, something very funky over here that we're just not going to worry about for this class, okay? And then, well, we've seen this before, but we've got a little bit of a new plot here that you might see, I will pretty much always give it to you in histogram form, where you are looking for this relative normal distribution there. This one's a little clunky, maybe more so like that, but still, no biggie. Still looking for the same stuff. With this plot, this is called, and I put it on here only because it is becoming more common to report rather than the histogram, but this is called a QQ plot. And the general idea here is that you want all of these dots on the line, okay? That's the general idea. Again, I will pretty much always give it to you in this form, but this is not our data. This is the residuals. Okay, so even you could just freaking fast forward through this and just say give that a big FU, and we're going to stick with the histogram here. But the general idea with this is both telling you the same thing, just in a slightly different kind of fashion. You might see this out in the wild, but more likely than not, you'll see this. So no biggie. No biggie. So those were two normal distributions. These are two very much not normal distributions, right? So you can kind of see here that none of these dots are on the QQ line here at all, right? They should be like that. And then this thing over here is like way left, or is way right skewed, right? So that is no good, right? We would have to do something different to our model. Now, in this class, I really care about the overall interpretation of your general linear model, your regression model. I likely will not give you anything that looks like this, just because it's not. I don't think that is very helpful in learning, right? But do keep an eye out when you're doing this in real life. Do keep an eye out for this kind of stuff. Okay. So let's we'll pause the video again. Yeah, we'll pause the video, and then we'll pick back up here in just a second. So see ya in just a bit.